And just for reference, that's one sleep station. This one is another. Reheating. You want to ceiling if you want to call it. Right there. And there's a floor. On the other wall over here. So all of us need a little bit of. All right. I'm back. There's more to show you.
Okay, shall we start? ISS. All right. We are going to do an estimate. The estimate is curvature. In particular, one effect of curvature that is geodesic deviation. Geodesic deviation here. The problem here is that you hit the ground too quickly, and so you cannot easily see the effects of curvature. ISS, you have all the time. I'm saying time, so what's the time scale? How long do we have to wait to see that something changes, like ball of dust changes in shape? Do you have a sense? Milliseconds, years, centuries? We want a number, okay? Number in the sense of estimate, something I can do in my head or at the blackboard in less than 3 minutes, okay? Sign up. I think there are just enough slots. So 3 people, 3 slots left. First come, chooses. The one on Thursday is exactly the same that I'm doing, not for curvature on Earth produced by the Earth, but curvature on Earth produced by the sun. It is ocean tides. Today, no ocean tides, but the technique is the same. Okay? Okay, let's see if I can do it. You have a timer. Nobody set up, so I'm volunteering. I don't know if it's clear. No, like I was hoping somebody would do it, but you know, maybe I should. Yes.
You want all of us to sign up maybe once per section, right?
Once per section, and there should be like 1 or 2 spots free, and you can do it again, or if somebody wants to jump in, does it again. Yeah, sometimes it's useful that I do one to show you like maybe a trick or a technique, but I don't have to. I mean, it's totally okay that you do one and then we discuss and I give you suggestions, or I show you how I would do it. After all, 3 minutes is easy. Okay, so let's do it. 3 minutes. So what do I have to do? Geodesic deviations. So I need to know curvature, and rho sigma. These are dimensions of length minus 2. This is the length that I want. How do I know that it has these dimensions? Well, it's 2 derivatives of the metric. That's length to the minus 2. In particular, this is geometry just outside the Earth. So Schwarzschild geometry. So this is 2 derivatives of Gm over R, which is Gm over R cubed, 2 derivatives of R. So if I want a curvature length, it's the inverse of this square root. This is my definition of curvature length. R cubed over Gm. And you see, I know special relativity. C is 1, I put it back when I need it, but G, it's there. Okay? And I need numbers. So this is for Earth. 2 GM for Earth, we all know. Centimeter. Good to have it as easy numbers. 10 to the minus 2 meters. And then radius of the Earth. This we also all know. We have it in our list. 6,400 kilometers is 10 to the 7 meters. So here you have square root of 10 to the 21 divided by 10 to the minus 2. This is meters. So 23, this is 11 for me. 10 to the 11 meters. This is a number that I recognize. This is 1 astronomical unit, 150 million kilometers, 10 to the 11. So this is 1 astronomical unit. That does it. Curvature length here on Earth for in the ISS, 1 astronomical unit. But I want a time, tau curvature. So what I need is, if you want, L curvature divided by C. How long does it take light to the sun and back? 8 minutes times 2. So this is 8 minutes. So in the ISS, if I have something like free, like a ball of dust, let's say coffee powder in a ball, this is going to change in shape over a time scale of 8 minutes. And I still have 10 seconds left. Yes.
Why does the speed of light, like dimensionally it makes sense, but how does the speed of light determine the time scale of, let's say, a free dust ball?
Okay. I estimated the curvature.
Yeah.
This is the only scale.
True.
Okay. This is not very useful in this room or in the ISS.
Right.
You are not going to see 1 astronomical units effects. So one would say there's no effect because the scale is completely decoupled.
Right.
But maybe what's important is time.
Okay.
So now I have to convince you that time is important. So I'm saying I have this ball of dust. It's small, it's 10 centimeters, but I look at it for long enough, for 10 minutes. And I should see in 10 minutes, geodesic deviation is you prepare things all with the same velocities, and you ask if they remain parallel. Each one has 0 acceleration, but if there's curvature, they're gonna either deviate or converge. I didn't check the sign. I'm not telling you that it's converging or deviating. But the time scale, if you want, geodesic deviation, you could write it this way. Something psi nu. What's the thing that goes here? It's R mu mu. Tells you the direction. Then there's an alpha beta. Tells you the initial velocities. Okay? And so here there are 2 dots. Here there's psi. This has, I was saying, 1 over a length squared, back to 1 over a time squared, or if you want frequency squared, if this is positive. If it's positive, it oscillates. If it's negative, it diverges somewhere. Okay? Comments, questions? Should put a timer for questions so that we don't go over 10 minutes of questions. Yeah.
Where is the information of the dust forming the dust?
Good question. It's nowhere except for the statement that dust has no interaction. If it was a stick, if it was something rigid enough that it wouldn't deform, dust just means each piece, each speck of the dust is following a geodesic.
The size of the dust ball doesn't matter?
So the size of the dust ball doesn't matter, only matters that, yeah, okay, let me address that. There's a psi here and a psi here. So if you take a dust ball of 10 centimeters, this is gonna change in shape over this scale and deform. The bigger is the size, the more it deforms.
Okay.
Okay? Keep that in mind next week or next time when we do ocean tides. The size is the ocean or the earth. Yes.
So if we are on the ISS, this gas ball, it sees the same metric all around, right? So it shouldn't deform in the ISS unless the ISS is changing the distance from the Earth.
So I'm thinking of ISS in a circular orbit. And I'm saying, take a ball. This ball is going to deform. This is the statement. This is the statement.
It sees the same metric throughout.
Absolutely. It sees the same metric, and this metric is not flat. It has a curvature. So it's not oscillating like when there's a gravitational wave that passes. That is the time dependent. I'm saying this is just Schwarzschild outside the Earth. You can take it as just Schwarzschild. Okay? It's like the harmonic oscillator. The harmonic oscillator is not moving, but the particle in the oscillator oscillates. Right? I want comments on the number. Then we can also discuss, like, how did you know this? How did you know that? How did you know this? the number, did you expect 8 minutes? Did you expect minutes or hours? Is it a surprise? Before I was saying, is it a microsecond or is it a century? Is it lifetime of the unit? Where is this number coming from?
And it recognizes the light, the time it takes light to travel from the sun.
Yeah, so that's the trick that I use because I noticed one astronomical unit. But it's clear that in all of this game, the sun is never playing any role. So this was like good way of building mnemonics. You don't invent connections, you recognize. We learned that the acceleration here has a typical scale that is 1 astronomical unit, one light year. Now you know one new number. The curvature here is 1 astronomical unit. And now you cannot forget it anymore. You have to use it next time. Okay? But it doesn't have to do with the sun. It's just this number that we estimate comes just from things that have to do with Earth. So the number, yes, right. 8 minutes, I was fast because I already knew this number. Okay? But still, is it familiar? Should you know already it was this scale?
Should we expect like solar system size effects be like on like a human scale effect? What seems kind of
Some are, some are not. So why this one is? Maybe ask the question another way. Could Newton do this calculation? Because I'm showing you how to do it. General relativity, geodesic deviation. But the curvature is small. Could Newton do this calculation? Or maybe I should be more precise. Did Newton do this calculation and put it in the Principium?
You did relate to the Keplerian time for the orbit.
Yeah. How long does it take to the ISS to make one orbit? You have to know the number. You have to know. How often does it pass above your head? Every 1 hour and a half, every 93 minutes. Okay? This is an estimate. Less than 3 minutes. I got 8 minutes. I didn't put a 2 pi. You want to see what is so how do I get a period? Period is 2 pi Kepler, say Kepler. 2 pi times square root r cubed over gm. You have all studied this formula. You know how to derive it. Pi, it's a period. What did you expect? That I cannot guess, but I can remember easily it's a period. This one is 93. So now I can address also the question of, really this pole does this? Do I believe it? So I can convince you in a Newtonian way, but then go back and think about what geodesic deviation is. So this is Earth. You know, ISS is just 400 kilometers above, so very close. Yeah, let me make it bigger, otherwise we don't see it. Okay, I'm exaggerating. Make it spherical. This is the orbit of 93 minutes. Now here I have my ball of dust, so it can be a bit above or a bit below, but all with the same velocity. If you are here with the same velocity, or you are here with the same velocity, what do? If you are above, you do this ellipse. If you are here, you do this circle. If you are below, you do this other ellipse. The ellipse is the geodesic. So you start with a speck of dust here, one here, they meet here, then they meet here, then they meet here, then they meet here. That's your oscillation. Is it 8 minutes? No, it is 93 divided by 4 from here to here. 93 going down. Okay? Okay, now you know curvature. Next time, what I want to see is tides. How high they are, what causes them, how often they happen. But you see, the number is this one. You just have to do this calculation. Okay?
Well, Professor.
There's still 3 minutes for questions. You do appreciate how short was the calculation, no? I'm assuming that I know what geodesic deviation means. I'm assuming that I know to do dimensional analysis in general relativity. I've extracted already what are the relevant quantities. So object, why did you neglect this? Why you neglect that? Want objections? Because let me say it once more. The logic is not that I'm proving things. I'm not trying to be correct. I'm showing you how to be right. And in estimates, being right is more important than correct. In general, you want to be right for the correct reason when you do a detailed calculation. This is not a detailed calculation. This is an estimate. What you care is to get a meaningful number, the fewest number of steps. Yes.
You get the same answer or, because how did you know to use like, why couldn't you use like the Ricci scale, for example, 2/r² on the Earth and then use that?
Okay. Can I ask everybody, what's the Ricci scalar here? The value?
0.
0. Why?
Vacuum.
Vacuum. Okay, then one can correct it. Well, maybe there's some error. Yeah. Okay. So that combination is 0. This one is non-zero. Then there are the signs. Yeah, I didn't care about 52 or 53, but you know, Earth is that way. It squeezes me this way and this way. So there's a minus here, a plus here, and this one is bigger than this one by a factor of 2. Okay? And the estimate, just don't care about one of these things. You get a number, you see here 2. I was very, you know, you want to get a number. The question is not, is it 8 minutes or is it 100 minutes? The question is it milliseconds? Is it centuries? I want to discriminate orders of magnitude. After I have this, then I can ask other questions. One more questions. Yeah. Sarah.
I didn't have an objection, but when you explained, or when you said that next week you want to do the tides and you use the same numbers, did you mean you don't even have to bring Newton into it? Or you just use it?
So I'm going to be interested in curvature, so it's exactly this formula. But the radius and GM, we have to think again what they are. And so you could already ask now as an objection. Are you saying that the curvature here, I can estimate it without knowing the mass of the moon and the distance of the moon? Is it true that that's negligible? And the sun, can I neglect also the sun or not? Because I neglected it. Is it a correction? Is it big? Is it small? Like, why tides know about the sun and the moon? Do they know also about the earth? Curvature. And curvature is a nonlinear quantity. But here I'm treating one and the other, say, as if I could sum them. Can I really sum them? Oh, yeah, we are in a perturbative regime where the curvature happens to be the sum of the sources. And I just neglected all the sources there. So, you see, I have one astronomical unit. The question is, the length scale of curvature due to the sun, how big is it? I'm saying as a length is bigger than this. How much bigger? What's the error? Is it 1% the error? Is it 1 per million error? Those are the things I want to read. That you just know you don't have to compute. Okay? Let's know in general relativity a room on Earth in the solar system. Only then you can start asking, how about a neutron star and a black hole? Or the early universe. Okay? Good. We can go back to theory now. So the plan for today is to discuss the action for general relativity. I'm gonna work as if you're not seen this already. I know that you've seen actions for particles, maybe for the electromagnetic field, maybe also for gravity. And why I want to go back to the action? I want to go back to the action because the one that I know that some of you have seen is the action, the Einstein-Hilbert action. We want the Hamiltonian for general relativity. How do you find the Hamiltonian? The easiest is you start from the action, the Lagrange, and you get the Hamiltonian out. Okay? And so the plan is, first, I'm not going to assume that you know the action for general relativity. How do you get the equations of motion out of the action? Then action for a scalar field, for gravity, and then action in a foliation. I already told you to go look at Arnold, Deser and Misner, ADM. If you haven't done it, this is a good paper. It's old, still good. And Wall's book has a chapter on all that. So let me start from a few steps away. So the question that I want to ask you is, where do Einstein equations come from? No, you could ask the same question for F = ma. Where does it come from? And if you just ask the question historically, well, Einstein was looking at the geometrization of gravity together with matching Newtonian gravity. Hilbert was thinking in terms of action. Thinking in terms of action, you need help. You need to say action of what degrees of freedom, what are the symmetries. So we're going to take this logic. And independently of the picture that you take, like directly doing F = ma or Einstein equations or starting with an action, there's a question of, is it unique? Are Einstein equations uniquely determined by some principle? What are the terms allowed? Is the cosmological constant a patch, a fix that you're something that you're putting after you have found Einstein equations? And so I'm going to illustrate you a modern perspective. It's the perspective of effective field theory. In this perspective, you go through a number of steps. You first declare what is fixed, what is the background. Background, I really mean background structures. For instance, the dimension of space-time is fixed. It's 4. We are not going to derive it. I'm not saying that it cannot be derived. I'm saying you have to start from somewhere. We're going to start from a manifold that is 4 dimensions, fixed topology, even simpler, topology of space times time. We are also going to fix the signature, Lorentzian. We are not going to derive it. Once you have fixed this structure, you have to declare what is dynamical. So in Einstein's gravity, what is dynamical is the metric, that is a Lorentzian metric, and matter fields. Let's say a scalar field, electromagnetic field, other things. You could also have particles. I'm not going to put particles, but you could also have point particles. So the action is the sum of a purely gravitational term, that's the action for gravity, plus the action for matter that still depends on the metric, because when you just do matter, among the background structures, you take this one, you think of it as fixed, and you say there's a background structure, a geometry. And yeah, that structure is dynamical. Dynamical means that when you look for equations of motion, you adopt this action principle that is, you ask that the classical solution is such that if you perturb the classical solution, at first order, the action doesn't change. When you vary with respect to the metric, you get Einstein equations. When you vary with respect to matter, you get matter equations. You can keep going on with the game of why. Here I'm saying, where are Einstein equations coming from? And the answer that I'm giving is from this equation, action variation. Then I can ask again, where is this coming from? Any idea? My understanding of Nether's theorem is about symmetries, not about the equations of motion. Right?
Principle of this.
Okay, so that's the statement. So the question is, where does the principle come from? As soon as you call it principle, you say it's a starting point. And I'm doing the game of shall we make one more step?
Can you argue it has to do with like path integrals?
Yeah,
and
that's what I'm asking. If you say the path integral is equal to the action, and you ask, is there a classical regime? Classical regime is when this piece doesn't vary too quickly. That's the statement. So that's one way of thinking of where the action principle comes from. It's a statement of classicality. But they are called classical equations. Okay, so I still have to write the action. That doesn't give me the action. It just said that there's a quantity out of which I get the equations. So when I say effective action, I'm already taking this point of view of the action is not just given like equation 1 in a textbook. It's effective in the sense of I'm starting from something else and trying to identify what is a powerful, efficient, or effective way of describing the physics. So I fixed things that I cannot change, the manifold, identify what is dynamical, metric, and fields. And then there are a few more things. I'm going to require locality, that is, the action is the integral over the manifold. This thing is the Lagrangian scalar. This is the volume density. This is the Lagrangian scalar. Sometimes people put them together like this and call this the Lagrangian density. This is the coordinate volume. So I have this quantity. Then I'm going to require symmetries. General relativity is generally covariant. Mathematically means that I can choose coordinates as I want. They don't affect the physics. More mathematically means I can make diffeomorphisms, and diffeomorphisms preserve the form of the equations, or the action remains invariant. So how do you impose that this action is invariant when you make a diffeomorphism? Well, this transforms as a scalar. This transforms as an object that we can work out. E for x transforms with this Jacobian. This one is a density. If you check the definition, transforms with the inverse of this one. So the two cancel and this one transforms nicely. This one is a scalar, you integrate it and you get something is invariant. Check slowly, but that's the key ingredient. So we need a scalar. Now, next step, there are many scalars that I could write. I need an organization principle. So this is the second step of locality. When I say locality, I mean more than integral of something defined at a point. The thing defined at a point, something non local is something that depends on 2 points. But you can write anything here as an infinite Taylor function around this point. Think of an analytic function and ask, what's the value of that function somewhere else? You stay here, you take arbitrarily many derivatives, and you infer what happens here. And so when I say locality, I mean a bit more. So there are all these notions of from a microscopic locality, it depends only on the value at the point, or organized in the number of derivatives. Derivatives know about a neighborhood. The more derivatives you have, the more you can infer about far away. And so the logic is there's an organization principle. You write the action as a sum of terms organized in number of derivatives. Okay? So first term, no derivatives. You should use the names 0 derivatives, 1 derivative, 2 derivative, n derivatives. So expansion in number of derivatives. I'm using this word here, hierarchy. I have to go back and say more what I mean there. No? So all of these have to be scalars. So let's check what scalars I can write starting just from G mu nu. So with 0 derivatives, I can write 1 is a scalar. You could say I can, G mu nu has 2 indices. I want a scalar. I have to get rid of the indices. But I only have G mu nu. So for instance, I could do 1 index up and 1 down, and I contract them, but this gives me 4. I could do 2 down and 2 up. This also gives me 4. That is, I go back to 1. I could put square root of minus g. Looks like it doesn't have indices, but we already learned that this is not a scalar. And so the only thing that I can put here as first term is a constant. Then I can check how many things I can write with one derivative. Well, you can try. You don't find anything with one derivative. If you want, you'd already know Christoffel symbol is not tensor. That's with one derivative. Then two derivatives. Well, Christoffel has one derivative. If you take a second derivative, you can write Riemann tensor. Then you can contract indices and you get a Ricci scalar, which is scalar. Yes.
How come you put no on the term, and the first one derivative? How come that term doesn't work?
This one?
Yeah.
Yeah. So you see there's still one index free.
Oh, I see. Okay, has to be scalable.
Has to be a scalar. You can try to contract them. You always have to go back to the definition, what is a scalar? And yeah. And three derivatives, you don't find any one. Four derivatives, you find Ricci squared, Ricci tensor squared, Riemann squared. You see what we are finding? We are finding that the most general action up to four derivatives is a constant plus Ricci scalar plus a curvature. And now let's go back and do dimensional analysis. So action should better have dimensions of action. Energy times time, right? Yeah, if you want Hamiltonian dt integral, or if you want integral PQ dot, have a way of knowing always that this is dimensions of action. Okay? G mu nu, here there's some freedom. Here you have to decide how you count dimensions. Because if you have a length, you say this is a length, and the length you compute it out of ds, and ds is square root of g mu nu dx nu dx nu. You have to decide if this has dimensions of length, do you put the length here or here? Now, mathematically, it's nice to think of coordinates as dimensionless. After all, they don't contain any physics. They could be angles. And the metric as the one carrying dimensions. However, then G mu nu, or if you take a tensor T mu nu and the tensor T mu nu, these two are going to have different dimensions because you need some metric to reason it. So when you do dimensional analysis, my recommendation, what I do personally is coordinates have dimensions of length. C is 1, coordinates have dimensions of length, and G is dimensionless. Because once you do that, then derivatives are length to the minus 1, curvature independently of which contraction. You could take Riemann, you could take Ricci. They all have dimensions of length to the minus 2. Why? Because there are two spatial derivatives. If you want, R is dg squared. Let me be more careful. Gamma is dg. And R is d gamma plus gamma gamma. That means ddg plus dg squared. And so this has always dimensions of length to the minus. This one is also fast. This is dimensionless. This is dimensions to the 4. And so the Lagrangian scalar, so these dimensions, out of that I can find the dimensions of each one of these quantities. Okay? And so here is where if you want that this one is more important than this one, you need that these dimensionful quantities are separated in scale so that you can think of it as a ladder. And if you're in the solar system, you need only some. If you're doing cosmology, you need only some. If you're doing inside the black hole, you need. The more the curvature is important, the more of them you need. If you're doing cosmology, that is the largest scale, this is the most important, the constant, the cosmological constant. Okay?
Can we, since we are defining this theory as an effective theory, can we, if C1 and C2 are not unique, right? Because you could redefine fields and they would change, right?
Yeah, so of the three, there is a topological invariant, so it's only two that are independent, so you could choose. You could set this one to 0 and then these two. And there's a nice way of doing it that is you give a name to this one and a name to the one of Weil squared.
Oh.
Weil squared is 0 equals small in Friedman-Robertson Walker. So this one is difficult to measure. In this one, when people speak about inflation, speak about Starobinsky model, this is the Starobinsky term. So you could argue that this one is already measured. So we have measured A, B, C, but none of the others.
What is the W just
Weil tensor.
Weil tensor?
We're gonna get
Type this C.
Yeah, C, you can call it C. Okay, so if there's a hierarchy of scales, we don't need to measure all of the couplings at once. Start from large scales, we measure G Newton, we measure lambda, and we hope that the reason why this works well is because the others are separated by orders of magnitude. And all of the logic of effective field theory is hoping that scales are separated, because once they are not separated anymore, you cannot use this logic anymore. Turns out that the world is a lot like this. No, Galileo didn't need to know about curvature. Newton didn't need to know about h bar. That's because there's a separation of scales. You can discover physics a bit at a time. Okay, so that concludes this part on logic. Then now we start with scalar field. Are there comments on this logic? So all we're gonna do is to cut it here. Okay, linear function. That's what we're gonna do. Okay, so then let's go back to something easy, something that I'm assuming that you have seen, and it is how do you write the action for a scalar field? So, and this is a scalar field in an external geometry curved background. Well, you need a scalar field, you need an action. Here, if you put a constant, the constant cannot depend on the scalar field, so no contribution. One derivative, you cannot write anything. You can write these things that are powers, these are potentials, and you can write things with two derivatives. This piece is what you call kinetic term, this piece is what you call potential term. Let's check that I'm putting the signs correctly. If I don't have this, if I don't have a book, if I don't have a notebook, can I trust that I put the signs correctly? This is T minus V, kinetic minus potential energy. That's the Lagrangian. The energy is kinetic plus potential. The Lagrangian is kinetic minus potential. The signature is minus. You see that this one makes it positive. No, because this is a phi dot square. So this is positive. This should better have a minus. Okay? You know, you might be taking another class where people use mostly minus signature. How do you know which one is correct? T minus V. No, that's unambiguous. Good. How do you get the equations of motion? So I'm going to go through this quickly, because then we have to do it for gravity. That's where I should go slowly, but let me do it. Why I'm doing it? I should say that, because one could say, oh, but I know that the action gives me Euler-Lagrange equations. I've done it that once and for all. So now I remember Euler-Lagrange equations. I just have to use them. And I'm suggesting that you rederive them every time, because those you have derived them once for a particle in a potential without worrying too much about regions, about boundaries, about boundary terms, about which ones are the variables. And the derivation, the theorem comes with a list of assumptions that every single time now you don't know if they are satisfied or not. And it's way faster just to redo the proof every time, because the proof is not long. And it also explains what you're doing. So equations of motion from the action just by varying. I show you the way I do it. I say I have my action, and now I want to find classical solutions. What are classical solutions? They are configurations such that if I vary them a little bit, the action doesn't change. So that's what I'm saying classical. Classical means such that if I do phi plus epsilon perturbation, and I do a Taylor series in epsilon, and I truncate the Taylor series at linear order, this linear order is automatically 0. This is whatever it is. Then there's a linear order that I require to be 0. And second order, I'm not saying anything about second order. Okay? Equations of motion are not about second order. It's a separate question about stability. Okay? So let's do it. And you see, what does it mean, epsilon here? It just means that I'm doing a variation. Functional variation just means put a parameter, do the Taylor series in the parameter, and then keep track of terms. Okay, so we have the action. The action was written here. When I vary it, there are two of them. So when I vary, I cancel this factor of 2, and I just get a delta phi here. The delta phi here. At this point, becomes useful to think of these are partial derivatives of a scalar. So I can put for free a covariant derivative. The reason why it's nice to have a covariant derivative is that you can turn it by parts. It goes through the metric, and you get a piece, the one now where you turn by part the covariant derivative, that is just the Klein-Gordon equation. And a piece that is a total derivative, that is 0 if you have fixed the field, the variation on the, if you have fixed the field on the boundary. If you vary inside without varying the boundary. Does it look familiar? If it doesn't, work out F equal ma out of the action for a particle in this way. There's another thing I should say, that is when you took mechanics, you probably, all the emphasis was on the Lagrangian. I'm not speaking about the Lagrangian, I'm speaking about the action. The action is better than the Lagrangian. Because in the Lagrangian, you have to be, you see, I turned things by parts, and either I dropped them or I checked that it was 0. It's because the Lagrangian is under an integral. If you work only with the Lagrangian, then you have to be formal on what you do with these total derivatives. Write the action. Don't work with the Lagrangian. That's my recommendation. Okay. One more thing. Energy momentum tensor. The energy momentum tensor there are many ways of defining the energy momentum tensor for a field on a given background. For instance, if the background has symmetries, you could use the symmetries and use Needler theorem. But here we are not assuming that there's a symmetry of the background. There's some general metric. And the thing that we're going to call energy momentum tensor that I should convince you of is that this is just given by the variation of the action for matter with respect to the metric. So let's first compute it, then we discuss why. Now, there are a few tools that you need to familiarize with. One is, if you know what is delta G mu nu, do you know also what is delta G mu nu at two indices up? Well, there's a way to find what it is. It's not just raising the indices. There's a minus. It comes from the trace condition. And there's another thing that is useful to know, that is what's the variation of the density. One way to prove it is you just use the definition of determinant. Okay, so now let's do this variation. The variation on the action with respect to G mu nu. How do I do it? It's the variation of the Lagrangian plus the variation of the density. The variation of the Lagrangian gives me a piece. The variation of the density gives me another piece. And so in general, I have the T mu nu is of this form. I can put in the Lagrangian for a scalar field, and I get this energy momentum tensor for the scalar field. let's check that it makes sense. So what's the meaning of energy momentum tensor? If you have a word line and you take the forward velocity of that word line and you take energy momentum tensor contracted with the forward velocity with a minus, this is the energy that a detector carried by this word line, or a detector that has this word line would measure the energy density. So this gives you the energy density of the scalar field. And you can check it's kinetic plus potential. Okay? And check that you know also how to do all the others, the pressure, the energy flux, stresses. Okay, I'm gonna go now to gravity with matter, but I should slow down. I should not assume that you're familiar with all these steps. I should also remind you that the homework goes through these steps. You have to fill them in, so make sure that you fill them in. Other comments?
Say something more about the Lagrangian of the scalar field, like what is phi?
Yes, yeah. So I'm saying that there is a scalar field. It's a real scalar, and what I did was just to declare this action, okay? Assuming that it's familiar. If it's not familiar, one can follow this logic that I was suggesting before of write every possible thing that you can write organized by number of derivatives. If you have no derivatives, you can write a function of the scalar field. You can still organize it in powers. If you require also stability, then it's a constant plus something quadratic.
Oh, so M is the constant A that we derive.
Yeah. Not exactly that A. So that was for gravity. Now I'm doing matter.
Oh,
Okay. And this is always this question of where do you start? So what I'm suggesting here is take this as a starting point. I'm giving you an action. This is the action for matter, and then there's an action for gravity. In the homework, you start from there and you compute out of that. So this one you have to buy. I'm selling it. But then it's fair to ask, where did I take it? How did I come up with it? Why this is interesting? So that's the logic of, can we think of it as an effective action? Does it appear in nature? One could ask the same question for the action for the electromagnetic field. Okay? So the homework as the theory part, it is action for gravity with a scalar field, compute the Hamiltonian. And so you are given this one. Okay? In a field theory course, you start with this and you learn that this is the mass of the excitations of the scalar field. Are there more comments? You know, we have 2 problem-solving sessions. They are made for filling in all the possible gaps that I cannot predict. I can guess some, but I cannot predict all of them. Okay, so now I'm going to do the equations of motion for gravity. This one, if you haven't, the ones before, you can guess the technique. This one takes a few more tricks. So suppose that I gave you this action. No, where this is going to turn out to be the cosmological constant. This is going to turn out to be 1/16 pi g. And I'm not putting them there yet because I want to show you that they are that. So if you're given this action, how do you find the equation of motion? Well, you just have to vary with respect to the metric. When you vary with respect to the metric, the metric appears in here and appears in here. So you need to know the variation of Ricci scalar and the variation of the volume density. So these are 2 things that you prove separately. You prepare them, you get convinced of them, and then you use them. Okay? Once you have them, and let me read them. This variation is Density again, G mu nu times variation. This variation is, you could just think of it as Riemann Ricci tensor. And this one is a total derivative. So this is the part that is complicated to derive, but in the end it's the one that doesn't affect anything because it becomes a boundary term. So now I do the variation. There's these two terms and there's this term. You see what happens. There's an R mu nu here, and yet there's a B minus 1/2. These two together form the instant tensor. And the other is a total derivative. So if you assume that asymptotically nothing happens, you drop total derivatives because they are integrals on the boundary. Or if you say, well, I'm just computing equations of motion. Equations of motion are fix the boundary conditions, and that's what happens inside. Okay, so summarize, yes.
Do you
One,
like,
two.
do you like just arbitrarily choose a boundary here, or like is there any certain choice? Or
Yeah.
like
Good.
stay in the boundary term vanish?
Yeah. So yeah, I'm not raising the question. Next week, there's going to be 2 lectures that are all about boundary conditions and about why those are important for understanding what is energy. Okay? So yeah, I'm just doing, let's do as you always learned, let's not care about boundaries, but then we're gonna have to care when we think about energy of matter and gravity. Yes.
When we will do the Hamiltonian formulation, will we keep this boundary term or will we, because I believe boundary terms are not helpful when you are varying the action, but if you don't do that, you should keep it.
We are gonna discuss that.
Okay, okay.
We're gonna discuss that in detail. Sure.
Why do we vary with respect to the metric?
Okay, so you could vary with 2 indices down. You would find also equations of motion. This is a choice that I make because to me helps me reuse formula that I prepared. No, so I prepared this one with 2 indices up and this one with 2 indices up, so that here I get R mu nu down. I could have done the other one. It would be equally okay. Just the only thing to remember is that the one with 2 indices up and the one with 2 indices down, there's a sign between the two. So that's the only remark. And clearly, if you do the one with the indices up, you get Isert tensor with 2 indices down. Okay, so now let's put things together. The action is the action for gravity plus the one for matter. When you vary the part for gravity, you get instant tensor. When you vary the part for matter, you get energy momentum tensor. So all together, you get this quantity, where here there's Einstein, here there's energy momentum tensor. If you want to match with Newtonian gravity, this should better be 1/8 pi g. And this quantity that appears here is what people call the cosmological constant. And so what I'm saying is that both A and B are measured. Okay? Let's go ahead. Let's go ahead. Yes.
Can I ask a stupid question?
Go ahead.
Why in GR we believe the fundamental dynamical variable is metric rather than other things?
Yeah. Okay, so this falls into the class of questions about why. So in the logic, I declared it. It's allowed to ask the question, but let's not forget that I cannot find the answer within this setting. Yeah, I declared manifold is fixed, metric is my degree of freedom. Okay? Then one could ask, doesn't it make more sense to speak just about how I transport things and what are units of measure? That is, I have my accelerometer with a clock, and I have something for measuring rotation, a gyroscope. So this is having the frame field and the connection as independent. Einstein-Cartan formulation where you start from all the variables, and then it turns out that it's equivalent to metric if there are no things like fermions around or no sources of torsion. Okay, and it is important to admit also that they are equivalent in these cases, but the picture that you have in your mind, that you draw of the world, is completely different. The picture that we learn about what is general relativity it's a curved space-time, curved geometry. Once you make that step, you don't have a metric anymore. You just have a manifold and a notion of what detectors you can carry around and how you can compare their measurements. You only have a connection in the same way as for the electromagnetic field. And besides having a connection for transporting things, you have a scale, a local orthonormal scale. No? And this is a completely different picture of the world. That if you adopt, then you have to adopt up to the end. And we're not going to do Einstein-Cartan here, we're going to do only metric gravity. But for quantum gravity, it's powerful thinking about it. Then one can keep asking, why can we do something else? Can it come from something else? Okay? Okay, so all of this was about action and Lagrangians. I want the Hamiltonian. Why I want the Hamiltonian? Why it's powerful to have this other formulation? For many reasons. Hamiltonians come with a structure, with a space that allows you to tell you what is the free space of initial conditions, what is free to choose when you prepare a system. It allows you to speak about time evolution at given initial conditions. It allows you to speak about energy. I'm not saying that you cannot speak about these things in the Lagrangian formulation. I'm saying this is a formulation that makes transparent the answer to those questions. There's a price to pay. You don't see space-time anymore. You see space evolving in time. So if you're asking questions about space-time covariance, don't use the Hamiltonian formulation to answer them. It's a good exercise. It's a good test of consistency, but it's not the way to have those properties as manifest. Okay? So what I'm going to do is to do it for a particle to show you the logic, and then I do it for gravity. Let's do it for a particle first. What do you do for a particle? This one you are familiar with. This is the Lagrangian of a particle, kinetic term minus potential term, in one dimension. I'm not going to work with the Lagrangian, I'm going to work with the action. I'm not going to write Euler Lagrange equations, I'm going to derive them. How do I derive them? Well, I say, choose an initial time and a final time. Choose an initial position and a final position. Consider the set of all possible trajectories between the two. I'm interested in the one trajectory that is such that if I perturb it a little bit, the action doesn't change at first order. So you could do it slowly as x naught plus epsilon delta x. I'm going to do it a bit more quickly by just saying this just means functional derivative. So I'm going to vary the action. When I vary, there are two places where I can vary. That gives a 2 dt delta x. Here, there's a derivative of the potential delta x. Then this derivative, I can put it in front of everything and pay with a double derivative. This one, clearly, it's the integral of a derivative evaluates to the boundary. I had stated before that initial and final configuration are fixed. So this is 0. And what is left is f equal ma. F equal ma. Okay? Now, let's do the Hamiltonian. How do you do Hamiltonian? Hamiltonian comes with a lot of structure, comes with the logic of a phase space that makes some properties clear. If you are curious what are those properties, they are the classical version of what in quantum mechanics is unitarity. Okay? But before going there, there's something that you can say that is really low level, that is, oh, look, yeah, there's x dot squared. When I vary, I'm gonna get x double dot. Two derivatives are annoying if you want to do things numerically. It's way easier to do one derivative. How do you do one derivative? Well, you first give a name to x dot. Let's call it v. And then you say there's an equation for v and one equation for x. If I do it that way, I'm just lowering the number of derivatives. Hamiltonian formulation is you lower the number of derivatives in such a way that a new structure arises, the structure of phase space. I'm saying this because when you do it for gravity, let's not forget we're just lowering the number of derivatives. If there are no derivatives, don't try to lower the number of derivatives. You're going to just find things that don't make sense. Okay? Don't take the prescription literally, take the logic behind the prescription. Okay, so what's the prescription? You introduce a momentum conjugate to your position. It is the variation of the action with respect to the velocity. This is mx dot. You treat them as new variables. That is, you don't think of x dot as obtained from the position. You think of it as independent. And you write a new action. So you want an action that is equivalent to this one, but where x dot never appears. How do you do it? You write pq dot, and then you pay so that you get back exactly the Lagrange. I just described the Legendre transform without saying the words. How could I do that? Well, because I'm focusing on action, saying action is all I need. You can change variables, but the action should be the same. The thing that I'm gaining is this PQ dot here. This is all this structure of phase space that I was telling you about. PQ dot minus Hamiltonian. Hamiltonian is kinetic plus potential energy. If you're interested in energy, you read it immediately here. Okay? So now let's do it again. Can I get F equal ma, but not starting from the action, Lagrangian action, but starting from the Hamiltonian action? So what I'm promising is I'm going to get Hamilton equations, but not the standard textbook way, but just saying, I just need to have the action is stationary. So let's see. So now I have at the initial time, I have both P and Q. So you see these sections are not space, they are phase space. You have a point in phase space here and a point in phase space here, and I'm interested in a trajectory such that if I perturb it a little bit, the action doesn't change at linear order. So I have to vary it. I can vary with respect to P or with respect to Q. So I get an equation, delta P, delta Q. This should be true for all variations, delta P and delta Q. So I get one equation and another equation. And this is a total derivative that on the boundary is 0. So I just derived Hamilton-Jacobi equation. So now you see also why this -1 is there. You see where it comes from. Right? Yeah. And so you recognize that one is just the definition of P. P is m times velocity, and the other is Newton's equation, F equal ma. What did we gain by doing this? Well, we gained a lot. We got, instead of working with space and this, how things change at first order velocity, we got this structure that is phase space, that you can think of it also as a manifold. It is a manifold that has structure, doesn't have a metric. Euclidean metric is something symmetric and positive. It has something antisymmetric. You learn differential geometry. If you want to learn this, you have to learn symplectic geometry. If you really want to understand all of the logic of phase space. The way you have probably seen it already is instead of thinking of it geometrically, you say, look, there's this piece here, PQ dot, that tells you that Q and P are a canonical pair. Or if you want, if you introduce Poisson brackets that are defined so that Q with P is 1, just because they are these derivatives, then you have structures that are preserved. In particular, all of those equations can be written as Q dot is the transformation generated by H on Q. The infinitesimal transformation generated by H. That in the quantum theory is commutators. Yes,
Is theta sometimes called symplectic potential?
yes. Yes.
Okay.
Okay, let's do it for a scalar field, and next time we do it for gravity. How do you do all this for a scalar field? Start from the action. This one you buy. This is the same that I had before. I'm putting a generic potential here. Before I had 1/2 m squared by squared. I mean, it's for free. Just put V of I. We learned that the equations of motion is you vary it and you get Klein-Gordon with an external potential. So now what I want to do is to treat this, let me say, find the Hamiltonian for a scalar field. How do I find the Hamiltonian? Well, first to find the Hamiltonian, I have to find what is time, but there's no universal time. Last time, all of last week, what we studied is how you take space-time and you do a foliation. Introduce a notion of space changing in time. You need a metrical space, a lapse, and a shift. So the first step is you take the expression from last time, you plug it in here, and you find that you can write the action for a scalar field as a kinetic term, the usual potential term, and the derivative term that goes with the potential. You can check this is positive definite, so goes with potential. And you notice that the kinetic term is not just phi dot squared, because phi dot is in the direction of t, but yeah, this one is really the part that comes from the normal section. I'm not assuming that time as defines world lines that are normal to the sections. So I have both a lapse and a shift. Okay, so now that I have this one, how do I do the Hamiltonian? Well, I take my action, I vary with respect to the time derivative of the scalar field, and I get this quantity, and then I write my action as PQ dot minus whatever appears here, this is the Hamiltonian. And what are the equations of motion? Well, they're going to be Hamilton's equation. When you look at the Hamiltonian, you are going to find that, and this is one of the pieces of the open. You're going to find that it's written as energy density times the lapse times energy flux times the shift, where this energy density is defined with respect to these world lines that are normal to the sections. And this we're gonna need when we do the Hamiltonian for gravity. Should probably put up the homework. Yes, go ahead.
Yeah, so here, so the Hamiltonian formalism required space-time can be break into hypersurface in some time-like direction. If the space-time is not globally hyperbolic, it's not possible to do Hamiltonian formalism.
That's correct.
Okay.
That's correct. So we're gonna just assume it.
Okay.
Assume it, hope that get out of it as much as we can, and then when it's not true, ask what we have to change. So you can start the theory part of the homework. You are gonna need things that we do next time for the gravity part, but you see, I'm giving you the action for gravity, the action for a scalar field. I even put the boundary terms and compute the variation of the action with respect to permutation. If you want, you put the indices up here so that you use the formula that I have. Then find the Lagrangian action by putting in the foliation. Do it for the scalar field. For gravity, we're going to do it together next time. Then find the Hamiltonian action. And in particular, determine what's the Hamiltonian for gravity that we're going to learn in constraint. Okay. Yeah. What do you learn from these kind of calculations? There is one thing that is going to be completely clear in the end. That is, how many degrees of freedom does gravity have? Well, if you do perturbatively and you just look at gravitational waves, you say, well, there are two polarizations. But what if I don't do it perturbatively? I look at full gravity, full general relativity. How many degrees of freedom there are? And here you're going to be able to count degrees of freedom. Going to be still two, right? Now, perturbatively, you go back to two, and it's not that you kill any by doing that, or that you make something appear. And here you're going to do the calculation for gravity plus a scalar field. So you should find two for gravity, one for the scalar field. Q and phase space is those together with the conjugate momentum. If you need a motivation for working out the scalar field, if you are like, why are we doing scalar field? I want to do neutron stars, or I want to do electromagnetic field. I'm going to do cosmology. This is going to be the inflaton. I need all the pieces for doing the inflaton. Okay? Better to prepare it now. It's easy, and it's going to be important. There's time for a couple of comments, then we'll close.
Can you explain again where did the time derivative of the
Yes, I think I have it. So, I think if you go somewhere here, take this piece, you expand it in the TT part.
Oh,
Okay, and so this one now is a phi dot. You are varying with respect to phi dot. So you see, you are really taking something covariant and turning it into something where it's still covariant, but you cannot see it in the equations. The equations hide it.
Based on his question, so if you don't have a globally hyperbolic space-time, we can still set up the same things, just that the initial values can't be like propagated, right? Like you can't evolve the equations consistently. Is it that?
Yeah. Yeah. And so there are all the questions. So can we predict things? Can we predict what's happening? And there are a lot that one can say, like, can I predict what happens here tomorrow? Well, if I tell what comes from the window and what comes from the door, yes. So I cannot predict it only knowing what happens in here. This is one of the aspects. This is one of the aspects about boundaries. There are others. Okay, so we are just looking at the case where we have everything at the.
Right.
Yes.
What would be like a physical example and not globally remote?
It's not immediate to come up with examples. One could say, if you form a black hole, is it globally hyperbolic? Well, yes, it's globally hyperbolic. The initial conditions are such that you can predict things. Then you can keep predicting things. Things go bad only. Like we're going to work out the case of a rotating black hole or the case of a charged black hole. There's a Cauchy horizon inside. Cauchy horizon is the place where the Cauchy foliation stops working. But there's something earlier that happens that doesn't, like, if you neglect, that doesn't happen physically. That's the short. So it's a long story that we're going to discuss. We're going to work out the Penrose diagram of that and convince ourselves that we don't have a breakdown of predictability. It's only if we impose exact symmetry and we don't take into account perturbations, it looks like there's a problem. Okay, that's all for today. Thank you.
Thanks so much.
Eugene. Have something like for the